Get started. We're going to do this lecture on phase lock loops. We're going to talk about it at the top level. So we'll talk about the basic loop architecture, and we'll go through block by block. And for each block, we want to identify what it does and try and obtain some kind of linearized model for it to allow us to do a linearized analysis of the overall loop. And in doing that, we'll arrive at a design procedure for designing the various blocks in the PLL. So here's a cartoon picture of the PLL just to explain what it functionally does. Basically, we talked about this before, but PLLs are used to tune anything on a chip to have a precise frequency or delay. Okay, some type of loop is required to do that because anything on the chip that has to do with frequency or delay is going to vary with process, voltage, temperature. There's no equivalent of a band gap reference for those quantities on a piece of silicon. So the role of the PLL is kind of to do the same job as the voltage reference does, but for units of time rather than voltage here. So in order to do that, we need some kind of precision component that gives us something to grab onto, right? Something that won't change. And usually the most common thing that's used for that is some kind of off-chip resonator. So a crystal is commonly used for that. So a crystal with precise dimensions, like a quartz crystal, will have a resonance to it that can be excited with a small circuit when it's connected to a small circuit on the chip, and then that can produce an oscillation at the resonant frequency of that off-chip component. So that's kind of that circuitry, the active circuitry needed to do that would have to be on the chip. The crystal on its own is typically a passive component. Sometimes the circuits that are needed to make the crystal oscillate are integrated right alongside the crystal on a separate, package. But so that may or may not be the case. But the least expensive sort of component you can buy is just a pure passive crystal that then requires some active circuitry to get it to oscillate. Now, usually the resonant frequencies that are common or cheap, will just be whatever's available off the shelf. The cheapest ones will be in the range of tens of megahertz. And so it's not necessarily the case that that's exactly the frequency you need. You may need a different frequency than what's readily available or what's cheap enough, or you may need a frequency that can change with time. So that's a really common application of PLL. It's usually referred to as frequency synthesis because you're basically, on the chip, you're synthesizing a whole different frequency. You're not just using the resonant frequency of the oscillator at that point. So up here, we've got overall the PLL, and the PLL would include the voltage-controlled oscillator that's actually producing the output at the frequency we desire. But if it was left to run open loop, that VCO frequency is going to vary a lot with process voltage and temperature. So some kind of active feedback loop is needed where that output is compared to a reference provided by a precise component, and then that generates the control voltage and automatically adjusts it to maintain that precise locking. So here's the block diagram of it. There's a few components here, and we'll go through them one at a time, but the quick highlight that's obvious here is that it's basically a negative feedback system, right? So as with all negative feedback systems, the idea is that if you provide pi loop gain and you ensure stability of the loop, then you must be ensuring that the difference between these two quantities here is very, very small. So the only trick here is to consider what we mean by the quantities. What are the quantities at various points in the loop of interest? So physically, when we actually build the thing, then the quantity that we'll get out here is some kind of time varying voltage, right? The oscillating voltage, a clock signal that's going up and down. And the same goes for the input to the PLL here, maybe some clock waveform, so voltage also going up and down. But really the quantity that's being forced to zero in a negative feedback loop is whatever is being subtracted right here in the feedback loop. Like what two quantities are being subtracted from each other, and then that difference then being amplified through the rest of the loop. So in a phase lock loop, the quantity that's being compared is not, not really the voltage of these two clock waveforms. So it's not their voltage difference that's being made zero. What's being compared is the phase difference between them. So that's why the first circuit here is called a phase detector. It's comparing the phase of the clock waveform here with that of the clock waveform that's being fed back. And if there's any phase shift between them, then that's the quantity that's being produced at the output. An output is produced there proportional to that difference. That quantity is then amplified, and then we've got our negative feedback loop, so that if it's stable, that difference would be forced to zero. So we will see that the main topic that we'll study is a loop that's mostly second order with some higher order poles. So there's a lot of similarities to all the negative feedback stability analysis that we did, for example, for second order op-amp circuits. So that's good. A lot of those same ideas come in here. Let's go look at the blocks a little bit one at a time here. So the VCO is just the block that actually produces the output oscillating voltage waveform. Okay, we're going to commonly refer to it as a VCO, a voltage controlled oscillator. The idea being that the controlling input is a voltage, so that therefore the output frequency of the oscillator and its phase in turn is controlled by that voltage quantity. But it's also possible to have an ICO, so that would be a current controlled oscillator. So also sometimes called a CO, right? It depends if you think the V in VCO is like the units or the symbol or the word voltage. Anyway, so for current controlled oscillator, sometimes you'll see ICO, sometimes you'll see CCO. And increasingly common, you'll see that VCO replaced by, alternatively a DCO, which stands for digitally controlled oscillator. So in our discussion, we're going to focus on the use of VCOs there. But as far as the loop dynamics go, and what's required to stabilize the loop, the design, the sort of high-level design procedures, it all carries forward. It's just that the quantities are different, right? The circuit implementations obviously will differ, because for an ICO, you need to provide a current signal as its input. DCO, the input's actually a digital code word. So in that case, there's a bunch of digital circuitry here instead of analog circuits. But in terms of, what kind of poles and zeros are required to stabilize the loop, how the dynamics of the loop depend on those quantities, that's all, that our discussion will be pretty general so that it's applicable to any of those cases. But for now, we'll just talk about the VCO. So if we're thinking about a VCO, right, again, if we're going to try and apply linear analysis to the system, we need to come up with a linear model for the thing. So remembering that the quantity of real interest in the feedback loop is the phase of a clock, right? That's what bears the information really that we care about in a clock. It's not the voltage at any particular point in time. It's kind of the zero crossings. So, defined that way, what we're really interested in is finding a transfer function or linear response, a linear relationship between that voltage at the input to the VCO and the phase of the clock that comes out of it. So to kind of get at that, start out with this really general expression over here, where we recognize that the output of the VCO is actually a voltage, time varying voltage, Vos, and that can be written as a sinusoid, really without loss of generality. I mean, if the waveform happens to be more rectangular, that's fine. We can really replace that sine function with any function that's periodic with period 2 pi. So for example, you can go ahead and imagine that instead of a sinusoid, it's a rectangular square wave function that's periodic with a period of 2 pi. It doesn't change the rest of our discussion. Here, E is basically the amplitude of the oscillations. Again, it's not going to play a big role in terms of defining the dynamics of the loop. May be very important practically for building the circuit, using the circuit, but it doesn't come into play in terms of the ensuring that the phase is locked of the VCO. Okay, so if the VCO is basically a circuit that generates a clock whose output frequency depends on the voltage at its input, and in general, that voltage at its input is going to be time varying. Obviously, in a phase locked loop, we need to dynamically adjust that control voltage at the input. So that means that the frequency at the output of the VCO is constantly changing. It's a function of time. And we can generalize that. We can express that as shown here by just considering a phase phi that's a function of time. So it's time varying phase at the output. That's equivalent, as shown here, to frequency, or a time varying frequency at the output of the oscillator. So we have to be a little careful with notation here. We're defining this omega with the subscript instantaneous as being the frequency at the output of the VCO at one particular instant of time. It's can be a little tricky to define the frequency of an oscillator whose frequency is constantly changing, right? I mean, usually you kind of want to look for a little while and average out the frequency to know what it is. But so how do we define it? Well, we can define it by just saying it's however fast the phase is varying, right? It's the time derivative of the phase. Okay, so that would be the angular frequency in radians per second. So that's what we're doing here. We're taking the whole argument here of the periodic function, the sinusoid, taking the time derivative of it. And that time derivative is kind of, by definition, right? Really, this is by definition here, our instantaneous frequency. So you can see there's two terms, right? The way we've defined it. Omega naught is this constant term. So the idea is that that's sort of the nominal frequency that the VCO would run at. It might be somewhere around the middle of its tuning range, right? But that at any given point in time, the output of the VCO, the output frequency of the VCO will deviate away from that nominal frequency omega naught by some amount. And that's captured by the time variations phi here, right? So the omega instantaneous is the total number. Let's say the nominal frequency is 1 gigahertz, but it happens to be oscillating at 1.1 gigahertz. Okay, so omega instantaneous is 2 pi 1.1 gigahertz. But we're going to define omega. Simply omega is the difference between the nominal frequency, 1 gigahertz, and what it's instantaneously running at. So in this case, for the numbers I gave, omega would be 2 pi 100 megahertz. 2 pi 0.1 gigahertz, okay? So it's basically that deviation. So if we write it that way, right, then when we plug in for omega instantaneous here, omega naught plus that derivative of phi, then the omega naughts cancel, and you just end up with this derivative here. Okay. So all this is seems a little bit a roundabout way, but I wanted to be rigorous in showing that we can say that the VCO or any oscillator has a phase that's the integral of its instantaneous frequency, right? Should have made the time argument explicit there. Okay. So that's a key very basic point. If the sort of symbolic derivation here is not providing any intuition, another way to think of it is that, I mean, we can, arbitrarily define really the nominal frequency omega naught of the oscillator. It makes sense to pick it to be the actual frequency that's somewhere around where we expect it to oscillate. But in fact, mathematically, it's kind of arbitrary how we choose it. So let's say that we're kind of expecting this oscillator to run at 1 gigahertz, but we think it's a 1 gigahertz oscillator, but in fact, what we observe is that the phase is sliding a little bit to the right every time, right? Every clock cycle, it goes a little bit to the right. So if we write that phase as a function of time, so that would look like, with respect to that red clock over here, one clock cycle it's here, second one it's there, and every time this phase difference is getting a little bit bigger, right? The red is the nominal frequency that we're kind of expecting, and the green is what we're actually getting out, right? So in that case, if we wanted to plot that phase of that green clock versus time, where red is the nominal frequency, we would, we kind of get something like this. It's increasing with time, t. So now, if that continues for a long time, I mean, we know what's really going on. We know the oscillator's actually not running at 1 gigahertz. It's been running at 0.99 gigahertz or whatever, right? So that would be the same as saying that omega instantaneous is 10 megahertz below our nominal frequency. So actually, I should have reversed the polarity in here. Really, to stay consistent with the notation, we would define that as a negative phase, right, over time. And then we would say that, as I said, omega instantaneous is 10 megahertz below the nominal frequency. So omega is, minus 10 megahertz or something like that, negative 10 megahertz. So, and why are we getting a ramp in the phase? Because it's integrating that minus 10 megahertz over time. As we integrate it, we get this ramp going downwards. So that's, I think, an interpretation here of what the VCO is doing, right? That's really key. I think it's really important to recognize that the oscillator is this perfect integrator, right? So now, if we've designed the VCO properly, then that instantaneous frequency should be related, hopefully somewhat linearly, to the control voltage, V control at the input. So we can write this expression now, right? Omega is proportional to V control. So this suggests, these definitions suggest that omega naught should really be the frequency at which the oscillator runs when V control is 0. Okay? So if we wanted to be absolutely rigorous with this notation, but again, there's no loss of generality here. You can always imagine that there's a DC offset on V control, something like that, and this is a small signal model anyway. This whole thing is a linearized small signal model, so don't get too thrown off by that. There's no loss of generality there. So if omega is proportional to V control and phi is the integral of omega, then we can finally relate V control to phi by just saying it's proportional to 1 over s, right? The integral of V control. So, slide over here. So K os is this constant that relates V control to instantaneous frequency. So again, sticking consistent with this notation, it would mean that we should have a relationship something like this, right? Where the slope there is chaos. That's really what chaos is. Now, on most practical VCOs, that won't be a perfectly straight line, right? So you may get some bending of this curve. So that just means you have to take in, you may wish, if you want to refine the model to be more accurate, you may wish to take into account the fact that chaos is not a perfect constant, that it can vary. Because the slope over here might be a little different than the slope in other parts of the curve. So chaos is like that linearized gain constant, and then the 1 over s just comes from the integration of frequency and to phase. So if V control has units of volts, phi should have units of radians. So chaos, because it relates voltage to angular frequency, it should have units of radians per second per volt. Okay. And then the S gives us our kind of 1 over seconds here. That cancels out the 1 over seconds, and you just end up with radians. Okay, so here's our model for our VCO finally. It's basically an integrator with a gain of chaos, which is this gain constant. It's basically the gain constant of the VCO, the thing that relates the voltage to the output frequency. So the next component working our way around the loop is this divider here. So here we're assuming that we're doing the frequency synthesis application where we're trying to synthesize a frequency at the output VOS that's quite a bit higher than whatever reference frequency is available to us. So it's not straightforward to come up with a circuit that compares the phase of two clocks that are at vastly different frequencies, right? So one way that, the common way that people have come up with of doing this is to take the high frequency and divide it down, right? To turn it into maybe I should write this draw this with a different color. If this is our reference, then the idea is you take this output clock and you divide it down. That's the output of the divider. And now you've got two clocks that are around the same frequency and that you can compare their phase. So you'll notice it's there, it's the phase of the divided clock and the reference that gets compared, and therefore it's the phase difference between those two clocks that actually gets set to 0, right, by the action of the loop, the feedback action of the loop. So what it means that in steady state, if the loop's working properly, these two clocks, the divided clock and the reference clock, will be the ones that are in phase. And the divided clock is a divided down version of the output clock. It's divided by n. Uppercase n is the constant we use for that. So it means that the output frequency, FOS, has got to be n times greater than the divided down frequency. And in steady state, in lock, the divided down frequency will be the same as the reference frequency. So you'll see that that number n, the dividing ratio, is what actually determines the output frequency, right? The output frequency is going to be n times the reference. Just the same way, if you have a feedback loop with a beta, a certain feedback factor beta, right? Then if the loop is performing ideally, a negative feedback loop is performing ideally, you expect the closed loop gain to be 1 over beta. So here, the feedback gain is kind of 1 over n, this divider. So once the thing is closed loop operating properly, you expect the gain of the closed loop system to be 1 over n, or just n. And that's what you get. You get an output frequency, and in fact, we will see an output phase that's n times whatever the input is. So think about, we haven't talked about divider circuits yet, but it's not hard to imagine a circuit that does this. You can use some types of counters or just toggling flip-flops and lots of different ways these can be made. You can imagine anyway, conceptually, but this is functionally what it does. It takes the input clock from the os and then produces a divided down version of the clock out here. So the period of the output of the oscillator is labeled T0 here. So the period of the divide by 4 output is 4 times T0. That's obvious. But let's say that the output of the VCO has some phase delay with respect to time 0. Right? However we define time 0, there'll be this delta t, right? The sort of phase shift of the output of the oscillator. So that we would express that in terms of the phase of the output of the oscillator, not in terms of seconds. We prefer to express it in radians. So to express it in radians, we have to normalize it to 2 pi, right? As far as the output of the oscillator goes, T0 is 2 pi. So to convert that delta t into radians, we multiply it by 2 pi over, t naught here, right? So the output of the ideal divider is on the bottom there. You see it's assumed ideal, so it's perfectly phase aligned with the input to the divider. So if that's the case, then if we want to write the phase at the output of the divider, right, we have to normalize that same delta t, that same phase delay in seconds, with respect to the larger period, 4t0. In general, obviously, that number 4 would be replaced by whatever the divide ratio is, n, right? So this term here is the phase in radians at the input to the divider. So if we make that replacement, you see that what the divider is doing, right? The way the input phase to the divider is related to the output phase in radians is by this gain constant 1 over n. Okay? So it's just to convince you that if you have a circuit that's dividing the frequency by 4, that it's also effectively dividing the phase by 4. It's just a rigorous explanation for the fact that, now you're normalizing that time phase with respect to a longer period. So in terms of radians, it's less, right? That's all that's happening here. But it means, in terms of our linear model, okay, when we've got a block like this, that, again, physically we might go make that with some latches, or whatever we end up doing, but our linear model would look like this. As far as our linear model goes, the input's not of oscillating voltage, remember? It's a phase signal. It's the phase of that clock in radians. And the output that we're interested in is the phase of a divided down clock, also in radians. And so those two we've shown here. So the notation that as being used here is just to drop that subscript div. And we see that they're related by this scalar 1 over n. Makes sense that it's a scalar because anyway it's got units of radians per radian, so it's just dimensionless gain. So this is a simple model for the divider where we assumed here that there was, you'll notice that I said that it was an ideal divider so that there was no delay between the input of the divider and the output of the divider. That's obviously quite idealized. It's a simplification. So in practice, there's going to be some finite delay from the input to the output of the divider. At the very least, you can imagine it's some kind of clock to Q delay of some of the latches that are in there. Depends how you build it. But that delay can become important when we start talking about the bandwidth of the loop and so on. So I just wanted to point that out for now. If you wanted to take that into account in your linear model, you've still got this 1 over n, but you would just introduce a time delay in there as well. Right? For example, the linear model, continuous time linear model for a time delay is like e to the j delta t, right? Time delay. S. Okay. So finally, we come back around the loop to the phase detector. So this is some circuit that is sensing the difference between the reference phase and, here I wrote the output phase, but it's not really the output phase. It's the output of the divider. It's the divided down phase, right? And it's the idea here, since the output, it produces an output voltage or current, depends how you build it, but it produces an output quantity that's proportional to that difference. So if the loop's working properly, that difference should get forced to 0. Or at least that would be the case at low frequencies where we have high loop gain, right? As often the case, loop gain will degrade at high frequencies, so we can't ensure that there'll be 0 content there at high frequencies, but at least at low frequencies there'll be a lot of gain around the loop. And so that's why we get 0 average current or voltage here in steady state. So here's a popular implementation of a phase detector. It's called a charge pump phase detector. So remember, the goal here is to produce an output, some output quantity. In this case, it's current. That's proportional to the phase difference between its inputs. So the approach that's taken here is that you've got some logic that's comparing the 2 clock waveforms. That's the reference there. Let's say we've got the divided down version of that here. And it produces output pulses, logic pulses, here and here at PU and PD, where the width of those pulses is equal to that phase error. So again, it's, even though I haven't showed you what that logic circuit could look like, it's probably not hard to imagine that you could cook up some combination of logic gates that basically, based on these 2 clock waveforms, produces something, right, that looks like this, right? So again, here it's producing a logic pulse, the width of which is equal to that phase difference. Now, of course, as I've drawn it here, the phase of the divided clock is lagging that of the reference clock. It's also possible that the phase error could be in the other direction, have the other polarity. So that's why there's 2 outputs. There's one output. It's actually the pull-up output. So I'll circle that in green here, right? It's the pull-up output that will be active when the divided clock is behind. I call that behind, right? Because time's increasing this way. When the divided clock is behind the reference clock. And then there's another output, PD, that would be active and produce a pulse when the time delay is the other way, when the divided clock is coming before the reference clock. So at some point there's some ambiguity, right? You can imagine when there's large, once you start getting a phase difference of pi around pi, well, which one is behind, which one is ahead? So at some point, early turns into late, and then, instead of PU being active, PD becomes active. And those details depend on the specific logic circuits you use there. But there's no need to get too wrapped up in that for now, because, hopefully we will design the entire loop properly so that it's stable, and so that once it comes into lock, these phase errors should be very, very small. They're going to arise anyway because of noise and all that, all that good stuff, but they should always be small enough that that doesn't happen. They'll only be small positive or small negative phase errors. And so you'll get, at PU and PD, these narrow pulses coming out every now and then. So they, in turn, drive these switches, S1 and S2. So if it's the picture that we showed over here, that would correspond to, the PU switch going active. So that switch would turn on, and then we would see at the output a current IPD equals this, whatever that current source current is, ICH. Okay, CH for charge pump. That's why it's labeled ICH. So now that switch is only going to be closed for the duration of this pulse width PU, which in turn is only, the width of that is proportional to the amount of phase error we've got. So one way to think of this is that in this window of time, we're delivering, at the output, the current waveform here, if I plot it versus time, will be these narrow pulses. And let's say this situation persists for a couple clock cycles. You get current pulses like this, and so each pulse corresponds to one comparison of the phase detector, basically. For now, let's assume that the phase detector logic is only looking at the rising edges of the incoming clocks. You can cook up phase detectors to look at both edges, but anyway, let's keep it simple for now. So then basically what's happening is you can think of each pulse as being a packet of charge, right? Delta Q, that's the integral of that current over that window of time. And the amount of charge that's thrown out by this circuit is proportional, obviously, to that time difference between the two clocks, which in turn is proportional to the phase error. And so what's the proportionality? Well, we know the height of this is ICH, right? So if we increase ICH, then we're going to get a higher gain here, right? We're going to get more. For a given phase error, we're going to get more current, more charge coming out. So ICH is, like, as a designer, the knob we have to play with the gain of this circuit, right? Now, if things are reversed, right? If it happens that the divided clock is leading the reference clock, then in that case we'd get a pulse at PD, and then this switch would close here, and we would get current getting sucked out that way. So in that circumstance, we'd have, as far as IPD, the waveform IPD goes, that current waveform would have negative pulses. So some charge would get sucked off whatever the next circuit is. And again, the width of those those current pulses is proportional to the phase error. The height of those pulses is determined by ICH. So here's just some, one example of what the phase detector logic can look like. Basically, you've got some RS latches, they're being set by one clock and then reset by the other clock, so that if one comes before the other one, that latch is temporarily set before it gets reset. And then you have a sort of opposite thing generating the pull down. So I'm not going to go blow by blow through the circuit operation. As I said, I think, and then this is just one example. People cooked up other clever logic circuits to do something similar. But for our purposes, it's most important to understand this picture here, right? This is just a nicer sketch of what I was showing before. Showing here temporarily the divided clock is lagging. So the phase error in this case is positive, okay? So we start getting positive current coming out. Then over here you see there's something happens. The divided down clock changes. The VCO maybe got messed with. Somebody changed the control voltage, right, on the VCO. So the phase changed abruptly in the divided down clock. And now all of a sudden it's leading the reference. So we start getting negative phase error and then therefore negative charge coming out. So if so let's think about how to model this now, the output of the charge pump. What we're going to do is consider the gain from phase error, right? The difference between the two clocks, the divided clock and the reference clock phase in radians, and we're going to translate that into the average current over one clock period. So how much current came out during this clock period from the charge pump? It was this amount of current, right? ICH. But it was only producing that amount of current for a fraction of time equal to the phase error divided by 2 pi. Right? So that's the, as I said, the fraction of time, or the duty cycle, if you like, of PU. Now if we do a similar sort of analysis for one clock period over here, you get the same result, right? You've got a output here that's negative ICH, but the phase difference here is now also negative, right? So the negative signs, really cancel, and it's really got the same relationship. That's the average current over this window over here. So it means that we can say that the phase detector basically looks like this. It looks at the reference clock coming in. It's called phi in. Here's the output of the divider. It takes the difference between those and then multiplies the difference by this gain, which we're defining as KPD, which is ICH over 2 pi. So this is our model that relates the two clock phases coming into the phase detector to the current that comes out. Right? The output here is, we labeled it IPD, the phase detector output current. The only catch, which we'll come back to later, is that the model here suggests a kind of a average slowly varying current, right? So it suggests that the output would look like this, whereas the reality is, this pulse that it comes in these narrow pulses. So the model is not capturing this sort of high frequency behavior. So we'll come back to that later. But for now, just let's just proceed with this model that's capturing the sort of low frequency behavior very well. So then finally, last component is the loop filter. So far, right, we've got an integrator over here with some gain chaos. Over here, we've got something that's taking the difference between those two and just another scalar gain constant. So we've got some scalar gains in here, but really, in terms of, and down here, we've got a 1 over n, right? So we've got a bunch of scalar gains running around, but in terms of the dynamics of the loop, we've basically got one integrator. So if you think back to your linear control theory, right, you know that when you've got one integrator in a loop, that loop can be stable, no problem, and we know that such a loop can track step inputs, right? So if we had an output frequency that was matched the input frequency, right, they'd be in phase. If the phase changed abruptly, then the output of VCO phase would make a step to match it, right? And there'd be some time constant there in the settling time, but it would track. But with only one integrator in a loop, we cannot track ramps, right? So what does a ramp mean in this context? A ramp input would look like a phase difference between the reference and the divided down clock, and hence between the reference and the VCO output, that is steadily increasing with time. So we talked about that before. When you have a phase difference that's steadily increasing with time, what that really corresponds to is a frequency difference, right? A constant frequency difference. So with only one integrator in loop, what it means is that we cannot track frequency errors, right? You can actually make a phase lock, technically speaking, you can make a quote-unquote phase lock loop very simply without hardly anything in that loop filter. But what you end up with can track phase as long as there's some mechanism that's ensuring the VCO is at exactly the same frequency as the reference. If they're the same frequency, it'll put them in phase, okay? But what it won't do is it won't let them track in phase and frequency at the same time. So a loop with one integrator in it is called a type 1 loop, right? And what happens if you put a ramp into a type 1 loop? The loop is trying, it's still a negative feedback loop, and it's trying to do its best to make this quantity zero. There's still a lot of gain at DC, right? In an integrator, infinite in fact. And the VCO, it's not like a circuit, like an integrator that you make out of capacitors and resistors or something. It's a really ideal integrator. That's important to keep in mind because it's like this mathematical integration of frequency into phase. So it's a really good integrator. It actually has infinite gain at DC. It really does, right? So it's got a lot of gain. It would try really hard to track this frequency difference. But what you would see in the fed-back divided down clock is it would lag behind it, right? So maybe I can see people like gears churning, sparks flying from like undergrad, but that's what you get with a type 1 loop and a ramp input. It follows it, but there's a lag there. So what does that mean? That means that if you have a type 1 loop and there happens to be a frequency error between the reference and the VCO output, it will kind of work. You'll get at the output frequency will be the same as the input frequency, but they won't be phase locked, right? The phases signals will have this constant difference between them. So that's why it's a bit of a, usually you don't think of a type 1 loop as being a phase lock loop. It will phase lock if there's zero frequency error, but how could you ever ensure that? As soon as there's any frequency error, then what you get is something that's frequency locked but not phase locked, right? So sometimes you'll see these type 1 loops are referred to as FLLs, frequency lock loops, right? And they can be fine, right? If all you care about is the frequency, you don't care about the phase response. But we'll see that even in the simple application, the simple example I gave of a basic frequency synthesis application, you got a crystal at 50 megahertz and you just need a 2 gigahertz clock, right? You don't care about the phase. You might think you don't care about the phase. Well, there's the other reason you might care about the phase is that there may be noise, right? There may be phase noise on some of these signals, and whether you have one integrator or two integrators in the loop will affect how well you can track out that phase noise and cancel it out. So there's other reasons why you might want a real phase lock loop. So the bottom line is that just with one integrator in the loop, it's not enough to do what most people want. So then the loop, what we have to do is we have to put a second integrator in the loop filter. Right? So we go and put another integrator in here, and then we get what's called a type 2 loop, or type 2 PLL. Now, as I've drawn it here, right, we understand that we need a bunch of gain. We need a high gain around this loop to ensure that the tracking is very accurate at the input. But we already know that if we have two integrators in a loop and a bunch of gain, that's 180 degrees phase shift, it's not going to be stable, right? So then we've got a problem. So the way we fix that is we also, at the same time, we introduce a zero very cleverly in just the right place so that we stabilize this thing. So that's the basics. That's the basic design philosophy for the type 2 PLL. Then how exactly you do that, right? How do you put that integrator there? Well, we've already got, with the charge pump phase lock loop, the charge pump phase detector, we've got a current coming out of the phase detector, right? So it's kind of obvious how you're going to integrate that and turn it into a voltage. You're just going to throw it onto a capacitor, right? So there's your integrator. Now how do you go, I'll clean this up a bit, sorry. Now how do you go and stabilize this, right? There's two integrators now, you're no longer stable. You need, as I said, you need to put a zero in there somehow. So it turns out that, as is often the case, right, if you add a resistor in there in series with a capacitor, that somehow introduces a zero. So we'll pause there, and then when we come back, we'll do some more analysis to see exactly what gives rise to zero and how to calculate it and so on to get the stability you want.